All right, so let's look at some other methods to solve differential equations. Now we have a whole category, of solutions that we can find that fall under the general heading of substitution. We make a substitution on an equation that doesn't fit one of our patterns. So for instance, right now we know how to solve equations that either by separation of variables or using an integrating factor. Those are the two methods of solution. So if we can't use either of those two methods, it might be possible for us to make a substitution and change what the equation looks like and end up with an equation that can be solved with one of those two methods. And so we're going to look at a couple situations where that works here in this section, in section 1.6. Now, I want to just point out, we're going to just look at two of these types of equations. We're going to look at homogeneous equations, and we're going to look at exact differential equations. For now, we're going to skip over the Bernoulli equations. We don't see those a whole lot. We're just not going to worry about those. We're going to focus on homogeneous and exact. And so I mention that so that you can, if you're reading through the book, you will not get caught in those in the Bernoulli. Then we'll also look at some second order differential equations, right? Differential equations that have the second derivative of y in them. All right, so let's start with homogeneous. So we're going to look at homogeneous. All right, and we're just going to start with an example here so that you can kind of see the process, and then we'll talk about how you tell for sure what's an homogeneous equation. All right, so here's an example. Here's a differential equation we want to solve. 2xy dy dx equals 4x squared plus 3y squared, right? Now, once you see that y squared in there, you know that all of a sudden you're not dealing with a linear differential equation, right? So that eliminates using an integrating factor. You might also look at this, and it doesn't take too much time to look at this and realize, hey, there's no way I can separate the x's from the y's here. They're just too intermingled. So our two methods are not going to work. All right, so here's what's going to happen. This is an homogeneous equation. I'll tell you why it is here in a second, but here's what we're going to do. We want, we can fit all this in here. We want to take this equation and solve it for dy dx, and that's simple. Right, just divide both sides by 2xy. And if we do a little bit of work on this, right, we take the 4x squared, put it over 2xy, plus the 3y squared, and put it over 2xy. We end up with, in the first case, just 2 times x over y, plus 3/2 times y over x. Right? 3/2 times y over x. We'll do this. And now here's what's significant about this, and here is why. Here is part of the definition of what it means to be an homogeneous equation. Notice that after this simplification, I've got basically the variables are x over y or y over x. So if you can take your differential equation and rewrite it in the form, let's put this here, and rewrite it in the form dy dx equals some function of y over x or x over y, okay, then it's homogeneous, all right? And we can use this approach. Now you might be saying, well, why, we've got both y over x and x over y. Well, that's no big deal because this is just 1 over this. So it's really still just a function of y over x. The reason this is important is because what we can do is we can make a simple substitution. We can say, all right, let's let v equal y over x, right? And what that does for us is that gives us, let's write this way, that gives us this type of equation. Dy dx equals 2 times 1 over v. We'll put it like that for now. And we'll actually use a v. 2 times 1 over v plus 3 halves v. So if we make that substitution, we get a simpler equation by letting v equal y over x. So we're not bothered by the fact that we have y over x. We would love it if they were all y over x, if this was strictly a function of just y over x, because then everything would be a v. But we don't mind using 1 over v, all right? So, but that's a simpler equation, right? Especially when you compare it to where we started with. Now, we've got a little work to do because this substitution, we still have to deal with this piece right here. In other words, we're changing to v's, and it'll still be a function of x. X's can stay, but the y's are going to be a problem. We'll talk about that here in a moment as part of the substitution process. Okay, so that's the goal that's what we're looking for to indicate that we've got a homogeneous equation. All right, now we can even do better than that in determining if we've got a homogeneous equation. Because let me just tell you, if it's a homogeneous equation, then the way we're going to solve it is typically with that kind of substitution. V equals y over x. Sometimes we'll use v equals x over y. But that's going to be our substitution. Okay, so homogeneous equations, you're going to make this substitution, let v equal y over x after you've simplified it down to this point. And then you're going to proceed like I'll show you. But the question still on the table is there an easier way to tell if you're dealing with an homogeneous equation? So there's our beginning. All right, so basically what you want to do is you want to look at the terms, right? This equation has this term, and this term, right? And kind of a rule of thumb is this. The degree of this term is 2, right? Because you got a y squared. The degree of this term is 2. Now, we're looking at this term. We don't care about this. All we're looking at is the parts that contain x's and y. The degree here is really, that's a second degree term because you get 1 degree from the x to the first, you get another degree from the y to the first. So in short, all of the terms in our function are second degree, second degree, second degree, second degree. That's an indicator that we're dealing with an homogeneous equation. If all of the terms have the same degree, then it looks like we can try to solve it using this substitution. Now, to use this substitution, we are going to solve for dy dx, which gets us here, and hopefully end up with an expression that just involves x over y's and y's over x's. Okay, we'll do another example to solidify this, but let me show you, now that we're here, how we solve that equation. Well, the first thing, as I mentioned earlier, is we have to get rid of dy dx. Y is gone. We want y's gone. X is still going to be there because it's the independent variable. All right, so how do we get rid of y over x once we get to this point, right? Because we can't just jump in and solve that thing. We have to complete the substitution. All right, so here's what's going to happen. Starting with this guy. Starting with v equals x equals y over x. Solve for y. So that's pretty simple. That's just going to be y equals Vx, or xv, right? Solve for y. Now you've got to find dy dx. Okay, so now we got to find what dy dx is of this so that we can substitute it in there. All right, now the nice thing about finding dy dx is it's always going to be the same way. You know, it'll end up being the same thing if this is our substitution. Okay, but we use what's called the multivariable chain rule. All right, and we're going to use partial derivatives. All right, so here's what this is going to look like when we do this. We're going to take the derivative. We'll take the, let's see. We'll take the partial. The partial of y with respect to x. So the partial derivative. So you remember this notation where we use this little Greek letter? That's a partial derivative. So the partial of y with respect to x times the derivative of x with respect to x, which is just going to be 1. All right, so let's pencil that in right now. That's just going to be 1. So that's nice. Always. Plus the partial of y with respect to v times the derivative of v with respect to x. That's always going to be the case. If this is your, well, let's finish this out. So what that gives me, dy dx, so the partial of y with respect to x says treat x as the variable, everything else as a constant. So the derivative of vx will just be v. Right? We're treating x as a variable, v is just a constant. And then dx is 1. So we don't have to worry about that. Plus the partial of y with respect to v. Now we're treating v as the variable, x is the constant, so it's going to be plus x. Okay, that's the partial. Let me put arrows to these. So that's that. There's a 1 here. That's that. All right. And then the partial of v, or the derivative of v with respect to x, is just going to stay right there. Okay. Now the good news is this. That is always the case. This substitution always leads to this value of dy dx. All right. And so we're going to substitute that in for what it is equal to. This goes right there. All right. So v plus x dv dx equals 2, 1 over v plus 3/2 v. All right. And now we've accomplished our task of getting rid of the y's. So now our equation is in terms of v's and x's. X is the independent variable. V is a function of x. But we want to solve this equation. And hopefully this particular differential equation is one that we can solve using one of our methods, right? Using whatever method it is. Let's clean it up a little bit more because we're not quite sure at this point. So we have basically we need to get the derivative by itself, right? That's what all of the differential functions we've dealt with have looked like. Okay, so we've got that right there. And we can even, let's just go sideways here. We'll put that there to remind us to go this way. So that means x, we'll divide that x through, all right, here in a second, I guess. So we'll kind of squeeze it up here. X dv, I don't want you to get lost here. X dv dx plus 2 over v, I'm sorry, equals 2 over v, plus this will just be 1/2 v, right? 1/2 v. 3/2 v minus v is 1/2 v. Let's combine these two. right? And at the same time, we'll get crazy here. We're going to move the x over as a 1 over x. So 1 over x times these two combine, we get a common denominator of what? 2v. So it's going to be, it's going to end up being v squared. We'll write it like this. It's going to end up being a 4 plus what? V squared over 2v. Okay, so there's the differential equation in the form we're used to it, right? Where we've got the derivative on one side, everything else on the other side. Now, we've got two choices to solve this. Can we solve it by either separation of variables or using an integrating factor? We'll start with separation of variables, and we notice, remember, to be solvable by separation of variables, you need your derivative equals a function, and you need that function to be able to be separable. In other words, have just an x piece and just a v piece in this case, since we're dealing with x's and v's. So it looks like we've got an x factor times a v factor. And so that should be separable. We should be able to get all of the v's together and all of the x's together. So we'll do that right here. The v's, this whole thing is going to move to the other side through division. So that's going to invert it. 2v over v plus v squared dv equals, don't do it in this very ink. So let's try that again. 2v over 4 plus v squared dv is going to equal 1x dx, right? We've successfully separated those things. And so now we can try to solve by integrating, right? Not there, but there. We just integrate both sides. Now this left-hand side, it looks like we can integrate using u substitution with v, or u equal to 4 plus v squared. So that means du is equal to 2v dv, or dv is equal to du over 2v. So when we make our substitution, we end up with the integral of 2v over u, and then dv is du over 2v, and things are looking good. Those are gone. And that will equal, we can integrate the right-hand side. That's just going to be the natural value of absolute value of x plus, we'll put plus c for now, but we'll talk about that here in a second. The left-hand side, okay, so if we work this through, we integrate both sides, we end up with a couple natural logs, like we get here. Now, there's an interesting trick we can do here. That's just a constant. It could be anything, right? We could call it C, C1. We could call it things like A plus B. We could call it whatever we want. It just represents a number. So here's the trick we're going to use to make our life a little easier. We're going to call it natural log of something. Okay, natural log of something. Right? It's just a constant. It doesn't matter. That's just going to make the algebra simpler. Okay? Because what we can do now is just a little bit of work here gets us this. This is the same as natural log of c sub 1 times the absolute value of x, right? Using logarithmic properties to combine these two. And then I can exponentiate both sides and end up with this, v squared plus 4 equals c sub 1 times x, or the absolute value of x. I don't need a double absolute value, so we'll just put them on one side. Absolute value of x, and then now I can get back to my regular variables, realizing that v is y over x. And just one more little simplification gets me down to this right here, y squared plus 4x squared equals kx cubed as my implicit solution.